Okay, so we're working on constant velocity 4, and we are going to kind of work through this worksheet together. First part, we want to review the graph itself, this position and time graph. So it says, consider the position versus time graph below for cyclists A and B. All right, so we don't have any numbers except for 5 seconds here. That's fine. We can still look at it and analyze the graph. If we look at the y-axis right here, we know that that is in meters, so that is position. Okay, so we don't have any numbers, but we can tell that this is 0, this is the origin, and then we can see that line B starts a little bit away from the origin, a little bit away. So you want to think about these graphs kind of like maps with time on them. So the time here, as time ticks away, these bicyclists are going to be moving along this line. So you want to kind of keep that in mind, that let's get some lines here so that you can understand what we're looking at. If we look at A starts at the origin, and A is going straight, okay, up to here. Okay? Hold on just a second. I'm going to close that out. All right, so that is line A, and we'll go ahead and label that A so that we can be really, really clear. Right. Line B, let's get another line. Line B actually starts right here and only goes till about there. We can see straight across. That's an about. But when we look at that, kind of thinking in motion, there are no hills and valleys. There's no incline, there's no going up. This is straight line motion. So we want to be really clear on that first. Okay? And it's the time that it takes. So A went this whole distance in the same amount of time that it took B to go this whole distance. So you want to be really mindful that position is a straight line and time is time. So let's go ahead and answer the question. It says, do the cyclists start at the same point? How do you know? If not, which is ahead? So how could we answer that? Let's look and kind of think about it. They clearly do not start at the same point. Okay? And we know that because the lines don't intersect our y-axis at the same place. So let's go ahead and type something like that in. I will make this a little bit smaller. As the lines are at different places on the y-axis. And then it says, if not, which is ahead. Well, we can see that B is farther away from the origin. So that would be like B is getting a jump start. So we could say that B is ahead. And I put too many H's. Because it is away from the origin. Okay. All right. Make sense? Thumbs up? Make sense? Yeah? Okay. At time is 7 seconds. Which cyclist is ahead? How do you know? All right, like we said earlier, there's no numbers on this time axis. So we have to say, okay, if this is 5, I know that 7 has to be over here. So it's going to put here's my 7. We're going to say that. It's kind of arbitrary, but we'll just say that. So which cyclist is ahead? Which cyclist is farther away from the origin? It's A. Okay, because if we go straight up from 7 and then straight over to the position, it is higher than B at the same time. So we could go ahead and type in at time 7, cyclist A is ahead because A is higher on the y axis than B at time 7 seconds. Okay. All right, so let's look at C. Which cyclist is traveling faster at t equals 3 seconds? How do you know? All right, well, same concept with 7 seconds. This has to be 3 seconds over here. So we'll go ahead and put a little mark here. Okay. Which bicyclist is going faster? Well, first of all, did either one of them change speeds throughout this graph? If I'm looking at this, they're covering the same amount of distance over each amount of time. A doesn't change and B doesn't change. These are straight lines. So, which one is going faster at 3 seconds is the same one that's going faster overall. So, which one's going faster overall? Why do we say A? If we look, we have the same amount of time here, but A clearly went a farther distance. So you guys were talking about speed earlier. If I go a farther distance in the same short amount of time, then I am going faster. Okay, so we can label that. That's 3 seconds because A is faster overall. And then we could even add another sentence if we want to be really clear. It covers far more distance than B in the same amount of time. Okay. Now this one, are their velocities equal at any time? How do you know? This velocities speed word means distance over time. So if we come back to the graph again, we do notice that they intersect. So at 5 seconds, they're at the same distance. But does that mean they're going the same speed? What do you think? Well, let's kind of look at this. Okay. So we'll get our red color for A. At 5 seconds, A has traveled this amount of space. But at 5 seconds, B has only traveled this amount of space. So the question is, are they going the same speed right there? Well, no, because A has still traveled so much farther in that 5 seconds than B has. Right? So let's answer that question. The velocities are not equal at any time because the lines are straight. so the velocities don't change. And we can see that the distance traveled in the same time is different. Okay. All right, so if they're not the same velocity at that intersection, what is happening at this intersection? So picture it in your mind. If you're a bicyclist and you're right here at the start of A, and another person is a bicyclist and they're right there at the start of B, you're pedaling away. Right here at this intersection, what did you do? You passed B. So at the intersection, A is passing B. Okay, these are our trails made by our bicyclists. A is starting here, traveling. B is starting here and just travels. But A is passing B. Okay. All right, so we want to be really careful to know that we are trying to understand these graphs because you are going to have to read them yourself. Okay. All right. So now we're going to take that graph that we just looked at, which is now called the previous graph, and we're going to compare it to a new graph. Okay. So let's remember what we said, and we will see if we can get, we don't have an arrow, but we can make it an arrow. Okay. So in this case, we have A, I'll make sure our colors are the same so we can see it. It's traveling from here to here. Okay. Going in this direction. We'll add arrows this time. B is traveling from here. Oops, we didn't change the color. To here. Okay. But in the new graph, let's see what we have. In the new graph, we still have A. A is still starting at the origin. A is still going in this direction. Okay. A still travels the full distance. And then we have B that's going to start here. But what direction is B traveling this time? Let's think. At the beginning, B is here. At 5 seconds, B is now here. So in this case, since the line has a negative slope, so since the line is at a downward diagonal, we are going to be going backwards. And this time we only go that way. Okay? So notice that. When the line kind of slopes down, that means that the bicyclist is coming back towards the origin. These graphs can be a little confusing because we think that the bicyclist is traveling on this hill, but they're only traveling in straight lines. It's really important to differentiate that. All right. So, how does the motion of cyclist A in the new graph compare to that of A in the previous graph from page 1? It's kind of like one of those illusion pictures. What do you see that's different, or what do you see that's the same? A is actually the same. You see that line? It's exactly the same slope. It's exactly the same distance. So we could write A is the same line and travel or velocity. And then the B. How does the motion of cyclist B in the new graph compare to that of B in the previous graph? What can we say? So B is going the opposite direction from the previous graph to the new graph. All right. C, we can see here. Which cyclist has a greater speed? How do you know? Make sure you look at that time. At the same time, which one went farther? Both times. For the same amount of time on the graph, A went farther. So if I go farther in the same time, I have to be going faster. So A had a greater speed on both graphs because it went farther in the same time. Okay. All right, so we'll go back up and look at what is happening at the intersection of lines A and B. The same thing here. In this case, B started here and starts going this way. A started here and starts going this way, but right here at the intersection, what happened? They passed one another. Okay. Okay. All right, so which cyclist traveled a greater distance during the first 5 seconds? How do you know? If I go first 5 seconds, right to here, let's get a line so we can actually see it really well. We'll get a different color line. Which one's bigger? From the beginning of B to the yellow line, or from the beginning of A to the yellow line? A has traveled farther in the first 5 seconds. So A traveled farther in the first 5 seconds. Went a greater distance during that time. Or it traveled farther along the y-axis. We got to make that connection between y-axis and distance. All right, I'll let Potter put more answers on there so you can go. Give me a thumbs up if that kind of makes sense and you're sort of following along with the graphs today. Okay, good. Good. Give me a second to get those. All right, so pages 3 and 4 are asking you to do a little bit different thing with this kind of data. Same concept, different thing. So we're going to go ahead and do 3 together, but you're going to be expected to do 4 on your own. Okay, so let's look at 3. This looks a lot like math. Okay, we will survive. Robin, roller skating down a marked sidewalk, was observed to be at the following positions at the times listed below. So I'm going to get a circle so I can make points. Okay, and I'm going to make it pink. Okay, so at 0 and 10. So at the origin on the x-axis and at 10. Well, hold on a second. This is not marked. So if I have 1, 2, 3, 4, 5, 6 for time, each of these should probably be worth 2 so that I can, let's go ahead and try to mark that. So we'll say 2, 4, 6, 8, 10, and 12. All right. And then we'll get another, and we'll mark this side. What should it say? Well, let's see. We need 30, and there's 1, 2, 3, 4, 5, 6, 7. So we should probably go by 5s. I think. That'll work anyways. And we will. All right, so now we have a graph. Now we have labels on our y-axis and labels on our x-axis. And now we can find 0, and we can find 0 for time and 10 for meters. So at 0 time and 10 meters, that's where Robin was. At 1 second time, they were at 12 meters. So at 1 second, they were right here. Probably move that up a little. At 2 seconds, they were at 14. So right at 2 seconds, we were right under there. Okay. At 5 seconds, we were at 20. At 8 seconds, we were at 26. Okay. At 10 seconds, we were at 30. Okay. So I don't know about you, but I feel the compulsion to make this, to see if this makes a line. So we're going to use our yellow line again, and we're going to try to make it a little small so we can still see our dots. And every single one of those fits right on the line, and that's really hard to see with that yellow. So let's make it blue. All right, so that gives us some data. That is a graph. We've used the time as the x-axis, the position and meters as the y-axis, and they purposefully made it confusing by putting an x there. But you want to think x marks the spot in this case. The y-axis is always position. Okay, so we did A, plot the position time graph for the skater. How far from the origin, 0, was he at 6 seconds? How do you know? All right. Well, at 6 seconds is right here. We do not have an actual data point that says 6 seconds. So how can we figure out where they were? Well, we can definitely interpolate, so bring information from the graph. And we can say, well, at 6 seconds, they're at about 22 meters. Because the data points make a straight line. Okay? So at 6 seconds, the skater was at about 22 meters because the data points make a line. You could go further and say, and I can tell from where 6 seconds intersects the line, that we are at 22 meters right here. All right. I'll let you have a second to type that in because the next one we're going to talk about the equation of a line. Dun, dun. All right. Write a mathematical model, an equation to describe the graph in A. Okay, so what is the equation of a line? You guys know this. I know you do. It's somewhere in there. I'll help you out. It starts like this. Y equals, anybody? Mx plus b. Never thought you'd see that again, did ya? It's all right. We'll survive. So let's think about what is this? Well, we know that y is y. Y in this case would be our position. M is the slope of the line. So we're going to talk about that slope of the line here in a second. X is time, but what is b? B is your y-intercept. So we know that this line very conveniently intercepts the y-axis at 10 because we have a point that says at time 0, y is 10. So we can go ahead and we could say y equals, we'll leave it as m right now, mx plus 10. Okay? So we need to find that m. All right? So I'm going to put m equals slope equals rise over run. You guys remember that? Give me a thumbs up if you remember the slope business. We got some thumbs up, some sideways, and some people putting their head down. Okay. So rise is the y, run is the x. So let's try to get this into an equation that we can understand. We know this is y, so we're going to take the difference between 12 and 10. So let's go ahead and write it out. Okay, we'll say y sub 2 minus y sub 1. Okay. Let's see. What would that be? Well, that's going to equal 12 minus 10. So we know that's 2. That is our rise. So we should probably document that. So rise is 2. What is run? Let's find out. So run would be x sub 2 minus x sub 1. So the second one minus the first one. Okay. So what is that going to equal? 1 minus 0. Right? Because we had this x minus 0. So 1 minus 0 is 1. So now we can say that m, or slope equals 2 over 1. 2 divided by 1 is 2. So now we can go back And we can fill in our equation of the line. Y equals 2x plus 10. Okay, that was a lot of work thinking about slope when you're trying to think about position and time. Okay. So let's think for just a second, though, before we move any further. Let's go back. I know you don't want to, but let's go back to slope for just a second. Okay. I'm going to pick a different color so we can think about it. Okay. If rise is your distance, then we're saying distance over, what was our run again? Let's go back. Rise is distance. Our run is time. So distance, I don't know, kind of distance over time. Okay. What does that look like to you? What about those signs alongside the road that some of you are starting to pay attention to? The speed limit signs? What are they measured in? Miles per hour. What does miles measure? Distance. What does hours measure? Time. Distance over time. So, revolutionary moment right now. Make sure your eyes are open. Okay. Slope equals velocity. Slope equals your speed. Okay. I mean, in this case, it's a velocity because we have a direction, but slope is velocity. It's a lot of work, but we're going to actually use that math stuff for something. All right, now, let that sink in for a second. Was its speed constant over the entire interval? How do you know? Well, let's look at this graph. Did we make a straight line? Yes. So the slope down here at time 2 is the same as the slope up here at time 10. So we know that that velocity or that speed was constant because we have a perfectly straight line. All right. So we can go ahead and answer that. Yes, his speed was constant because the line on the graph is straight, or the slope is the same across the entire time. Okay. All right, so that was page 3. I want you to do page 4 on your own. Now, check this out. It's very, very similar. Okay. You're going to make a graph. You're going to answer some questions about the graph. The good part is it doesn't actually ask you about the slope again. Okay. So answer these few questions, and we'll come back to that concept of slope tomorrow. Okay.